Hi everyone, this is the second part of lecture 2, Introduction to Descriptive Analytics. Okay, after having the mean, median, and the mode as the central tendency measures, now we are going to consider the measures of position, percentiles and quartiles. So let's define first the percentile. Percentile would be a point in the data set that a stated percentage or proportion of the data set, the observations, would lie below that point. So, for example, let's say this is our distribution, okay? And we want to consider a 10% percentile. So 10% percentile would be a point like P1 here, let's say, that 10% of the data set or observation or the probability would be 0.1. Yeah, the 10% of observations would lie below that point. Okay, so this is the definition of percentile. So what are the quartiles? Quartiles are special percentiles which divide the observations into groups of successive size, each containing 25% of observations. So this is why we call this as quartiles. Okay, so here we have three quartiles: 25th, 50th, and 75th percentile. So, for example, let's say this is our distribution. Okay, and the Q1 would be here, which 25% of the observations or data points would lie below uh, below Q1, and then Q2 here is the point that 50% in total, 50% of 50% of the data points are lying below this point, okay? Or we can say between Q1 and Q2, we have 25% of the observations. And also Q2 always equals as median. So yeah, this is the definition of the median, right? Yeah. And Q3, let's show with different color here. So Q3 would be somewhere around here, Q3, which 75% of observations are lying below that point, okay? So yeah, as you see here, we define three percentiles with special percentages like 25%, 50%, and 75%, and these are called quartiles, okay? Okay, after having the quartiles, a measure can be defined here as interquartile range, IQR, and this is the difference between the third quartile and the first one. So it would be Q3 minus Q1. So this includes the middle 50% of the values, okay? In order to calculate the percentiles and quartiles, first we need to arrange the observations in ascending order, and then the location of the percentile would be obtained by this formula, okay? So in this formula, n is the number of observations and p is the value of the percentile. For example, if we want to obtain the Q1, then P would be 25, okay? And N is the total number of the observations in our data set, okay? After calculating the quartiles, we can visualize the quartiles and the range in a graph, which is called box plots. So box plot actually is a visual tool for five measures, which are the minimum, the three quartiles, and the maximum. So let's have it here. This is the minimum, and the IQR or interquartile range. So this is the IQR QR. So this point would be Q1, this point Q3, and the middle would be Q2 or the median. Okay, and this point, so here we have the maximum, here we have the minimum, we have the range. Okay, but usually instead of considering the minimum and the maximum of observations in the sample data, we will consider the minimum as Q1 minus 1.5 times the IQR, okay, and the maximum as Q3 plus 1.5 times the IQR. So any observation lying beyond this range, I mean the minimum and the maximum, would be considered as outliers. Okay, so these are the outliers here. So in our analysis, we can obtain the outliers by this, and then we can remove the outliers for further analysis in order to reduce or eliminate the impact of outliers on our analysis. Okay, so this is the shape and the application of box plots. So far, we had the central tendency measures, mean, median, and mode, and also the quartiles. Although knowing those measures are very important, but they don't give us any information about the distribution of the data. In order to have an idea about the distribution, we need to go with measures of variation or measures of dispersion. So what's important, because we may have same mean value for different data sets, but maybe the distributions and the range of those data sets are completely different. So it is important to have the measures of variations as well. As I said, we may have different data sets with the same mean value like this. Consider these distributions, for example. And another one. So as you see here, the mean value for all these three data sets are exactly the same. They have same mean, but as you see here, the distributions are completely different. So because of that, having equal mean doesn't mean that those data sets are the same. We need to consider the measure of variation as well, like the standard deviation or variance. Okay, or another case here, let's see into data sets like this. So here, approximately, we can say the standard deviation or the measure of variation among these two data sets are almost the same. They have same standard deviation, but as you see here, the mean, let's say this is for the first data set, and the second one, the mu2, and as you see here, the mu2 is significantly greater than mu1. So in these cases, assuming just the mean as a base for comparison would work for us. But when we have this kind of case that the means are the same, but we don't have same standard deviation, then in that case, considering the mean as a base for comparison wouldn't be valid. Okay. Here are the measures for variation range. The range actually is the difference between the max and the min in the data set. Okay, so the variance, standard deviation, coefficient of variation, and interquartile range, which is the Q3, the difference between the third quartile and the first quartile. So Q3 minus Q1. Okay. Variance and standard deviation. The definition for the variance is the average of the squared deviation of the values from the mean. So here we calculate the mean, let's say x bar, or the mu, and then we take every observation xi and calculate the difference between xi and x bar, or the mean, and then we take the square of these deviations, and then we take the average over those deviations. Okay, so here we have two types of variance or standard deviations, sample and the population. So if we have all data of the population, then we calculate the population variance and the population standard deviation. We usually show this by sigma square and sigma as for the population variance and the standard deviation for the population. But that's not the case in the most of times. Usually we have a sample data. So for sample data, we calculate the sample variance and the sample standard deviations. So here the definitions are exactly the same, but we have slightly different values here. For the sample variance here, as you see here, we consider the x bar as the average or mean for the sample data, and then we take the xi minus x bar as the deviation, and then square of those differences, and then we take the average. But here, as you see, we divide the sum of over the squared deviations by n minus 1, not n. Yeah. For population, we consider n in the denominator, so it will be a simple average over the deviations. But here we consider n minus 1, and that's the reason we say that there is a slightly difference between the sample variance and the population variance. So in Excel or any other softwares, we need to consider the sample variance, S squared. We show this by S squared, and the S as the square root of the sample variance as the standard deviation. Okay. Another measure for variation is coefficient of variation, CV. So it's a relative measure of dispersion in percentage. Okay. So actually it says us how large is the standard deviation relative to the mean. So here if we have the sample measures, then CV would be S over X bar times 100%, okay? Or if we have the population measures, then CV would be sigma over mu times 100%. Let's have an example here. Assume that S for a data set is 3.1, okay? And the X bar, the mean, sample mean, is 9. Then the CV here would be 3.1 over 9 times 100%, okay? This becomes 34.44%. So that means the standard deviation is 34.44% of sample mean. So this is a relative measure. So as you see here, the CV is expressed in percentage, right? It's in percentage, so it's unitless. So there is no unit for the coefficient of variation. So since there is no unit for that, it would be useful to compare the variability of two or more data sets that are expressed in different units of measurements. Right? Yeah, even you have different units of measurement. In that case, if you don't normalize the data sets, then how you are going to compare the means, right? They are not comparable. In that case, you need to normalize the data sets, or you can use the coefficient of variation. Since it's in percentage, we can use this in that case. Okay, thank you.